All right, let's start. So my name is Vesa Karvonen, and I'm going to talk about managing state. I work at Reaktor, of course. Just a few words about myself. I'm basically a senior programmer. I've been programming for a very long time. More? Okay. Okay. So I've been programming for quite a long time already. But perhaps the interesting thing here is that I've been using functional programming for something like 16 years already. At first I was actually interested in computer graphics, and I worked at a game company for a long time. So actually web applications are kind of new to me, so that also makes them interesting to me. And what I was going to say that one of my special interests that has been for a long time. Saanko tän mikin jotenkin paremmin jos? Okay. I'll try to speak a bit louder. Don't know how well it goes with my voice. But my special interest for a long time has been programming languages and techniques. And when I say that it has been my interest, I mean that I've been studying stuff like type systems, semantics, and I've also implemented compilers. Also with at least a couple of contributions to an open source compiler called Milton. Nothing big really, but I've also implemented a couple of compilers on my own. One of them was just basically a very simple compiler, which we did approximately 16 years ago in OCaml. That's when I started doing functional programming. And then another compiler I implemented later, which also did all sorts of optimizations. And I'm also very interested in various kinds of programming techniques, like domain-specific embedded languages. So let's start with a poll, and there are certainly sort of right answers in the sense that I have an idea what is the preferable thing, but don't think about that. So I'm just going to ask which you would prefer, and and then I'll explain my view of it later. So do you think stateless things are better than stateful things? If stateless things are better, then raise your hand now. Right? Okay, and if you think that stateful things are better, then raise your hand. Ah, there are actually a couple of them. Okay. The thing is that programs are about state. You can't really eliminate it completely. If you have a useful program, it's going to have state somewhere. So the question isn't whether you should make everything stateless, but it's about how do you manage that state. Which parts of your program can be stateless, and where do you store that state? How do you manage that state? How do you make sure that everyone is consistent with the state? So you can't really get rid of it. So the second question, which is preferable, mutable state or immutable state? So if you prefer mutable state, raise your hand now. Okay. And then if you prefer immutable state, then raise your hand now. Okay, cool. So the thing is that the immutable state is really an oxymoron, because the essence of state is that it changes over time. So it's not really immutable, but you can certainly capture a moment in time as an immutable value from that state. But that's not really what state is about. State is about change. If you have a state machine and you have a finite state machine, then the essential state is the number of the state in that state machine. Or if you have mutable variables, then the state is in those mutable variables. And you can change those. And you can change the state in the finite state machine, and you can also change the values in those mutable variables. So which do you prefer then? Do you prefer having global state or local state? So if you prefer global state, raise your hand now. Okay, only a couple of. So if you prefer local state, then raise your hand now. Okay, so most prefer local state. I think everyone, the poll results were pretty much as I expected. So the thing is that one of the points that I'm going to argue today is that external shared global state is actually better than internal encapsulated local state. And there's actually a bit of a word play here, because global state doesn't necessarily make you think about external state or shared or internal state in local state. So the thing is that if you want to make something stateless, then it cannot contain state. You have to move that state somewhere else. And if you apply that principle, then what you end up is that all things are stateless, and you have state outside of all those program components. And then it's kind of global state. It's external to all the components. So global state is, in my opinion, the right answer here. So what is this talk about? First of all, this is not about any kind of new innovation. There are no new innovations in this talk. I think all the techniques are at least decades or several decades old. And there's this quote by Peter Landin that most papers in computer science describe how their author learned what someone else already knew. And where have I learned this? Is with my experience with Calm. And so what is this Calm? It's basically an architecture and libraries for writing reactive user interfaces. You can find it from GitHub. So you can see that there are like a bunch of libraries there. So there's documentation thinking about explaining how things work together. Then there's a lens library. Then there's like a library for reactive VDOM. And then there's this Atom library. There's also a Bacon version of that, but it's a bit simpler. It doesn't implement all the techniques. And this talk is mostly about this Atom library, in a way, about managing state. So Calm encourages use of external shared state and continuous observable properties. I'll explain that in detail later. But sort of the interesting thing for me has been to sort of the road to understanding why does Calm actually work so well. I've been using it in a couple of real projects already over the past something like, I started using it in late 2015. And it has worked really well. But like I said, these web apps are not something that I've been working on for most of my career. So I've been sort of wondering, why does it work well, and why other people are not doing the same things. So certainly Calm is not the only user interface framework that mainly uses observables. And you might have heard, for instance, about Cycle.js, or maybe there's this framework Yolk, which is probably not maintained anymore, and so on. And they use a slightly different approach. But in this talk, I'm going to explain why the approach in Calm actually works so well, and why the approaches in those other libraries might have certain problems. So when I was thinking about this talk and thinking about state, I came across this article, Local State is Poison, which is one of those nice things when I said that this talk doesn't contain any new innovations, then this is another example of that. This is an article by some programmer written in 2012, and when I read this just recently, it sort of made me think that, okay, this guy has understood all the same things, and it's so nice to have someone who actually thinks in the same way. And he also wrote another article, Why Not Events, where he argues against event-based systems. And this also rang a lot of bells for me. I'll make these slides available later, so you will be able to read those. You might even learn more about those, learn more from those than my talk. So certainly worth reading. So the goals for this talk are very simple. I just want you to think about state in new ways. So let's begin. What is state? So state is something that has a value, and it has identity, and it can change over time. So if we take some sort of axiomatic approach, then we might also say that if something has these properties, then it is also state. But what I'm mostly thinking about is just ordinary state in programs, like state that you have in local variables or global variables or in a database, for instance. And the truth is that state is quite hard. I think it was Rich Hickey in Simple Made Easy who said that state complex value and time. And I will also say that it complex identity also. And the thing is that identity and time are both quite complex. Tracking identities often complicates algorithms. So if you have been implementing web apps recently, you might have used React. And one of the things is that in React, when you render lists of things, you have to give keys to all the components. And the underlying reason for having to specify those keys is because it allows React to properly handle local state in those components. If those components didn't have any local state, then it would be reasonable to completely eliminate the keys. But because components in React can have local state, then it's important that React can sort of consistently move things around. When things move around in the list, it has to know which component goes where, so that the state follows with the component and also the component in the DOM. Also, change over time invalidates computations dependent on state. If you have a state and you take a snapshot of that state and compute something, then later when the state changes, then whatever you computed from those snapshots is no longer valid. So what you get that way is a lot of bugs. And in fact, just in the last project where I was working on, I was asked to fix a bug that was basically a result of that. So there was like it was a kind of a screen where you could buy things, and you could buy with various kinds of currency. And what happened is that if when you initially went to the screen, then you had selected like you would like to buy 2 things, but you didn't have enough money for that, then you couldn't buy it. But if you selected or unselected one of those things, then of course what you should get is that you would be able to then buy that one thing. But what actually happened is that you couldn't buy anything even after unselecting things. And the reason for that was that the component actually contained local state, which was updated in many places in the code. So what I did to fix that is that I actually deleted a bunch of code and then recomputed the property. But that's not, even though I was satisfied that I was able to delete code to fix the bug, it was not really ideal. Because what there should really be is that no state would be stored in such a way that it could not be observed and reacted upon. And that comes to the problems that we have in our current languages when dealing with state. So basically, what we have is that we have mutable variables and mutable fields in objects. And they are fundamentally second class. You can't return those from functions, and you cannot pass those as parameters. In fact, I think that a lot of you probably think that this even sounds crazy. How would you return a field of an object from a function? What that would even mean? Or how would you pass that as a parameter? But we'll see how that happens. And of course, we also cannot compose state. So if you have 2 local variables, then you cannot just say that, okay, I want a variable that contains the values of both of those variables. And that would also work as a sort of reference to those other variables. And also you can decompose. So if you have a variable that stores a tuple of things, or maybe a record of things, then you cannot just say that, okay, I want to sort of look at one part of that tuple, or one element of that record. And also you cannot observe those variables or mutable fields in most languages. Like I said, this is like in typical languages. There are languages where some of these can be done. So I think in Objective-C, for instance, it has some support for observing changes to objects. And also even as old as ML in the 70s had basically, it didn't have mutable variables as such. It had these ref cells, which are first-class objects, which you can pass as parameters and return from functions. But this is the case in most languages that we are using. So here's an example. And also this might seem a bit silly, but basically we have two variables, x and y, and they have the x has 1 and y has 2, and then we compute their sum. But then, then when we assign a new value to x, then the sum is still just 3. It doesn't change. And the reason why this doesn't work is that here we are actually taking a snapshot of state. We are copying state. We are not really depending on those values of state. And that's the sort of the root of making bugs with state. You take copies of state, and then the state underneath changes and things don't work anymore. So that's basically, so if I would boil the bug that I was explaining just a minute ago to its essence, then that's the bug. I fixed that bug just recently. About those limitations again. So here we're just creating a local variable. And then if you're calling another function with that value x, then actually this doesn't pass the variable itself. It only passes the value from that variable to the function. So if we, for instance, mutate the variable afterwards, then nothing inside that function could actually observe that. And also, we cannot return the variable from the function. It just returns the value of that variable. So can we make state more flexible and fun to use? And yes, we can. So here's an interface for state. And this is really the most simple interface I could think of it. And it only has two methods. So it has a get method, which returns the value of the state, and a set method, which you can use to set the state. In fact, in the libraries, if you look at the libraries that I'm sort of talking about here, then the interface there is slightly different. This is slightly simplified for this talk to make it easier to follow the code samples. So we can, of course, implement that interface in many ways. So a basic implementation would be just to give first-class state. So if you're familiar with Clojure, for instance, then you might understand the term atom here. So this is very similar to what would be a Clojure atom, or maybe what the ref cells are in ML or OCaml, for instance. So it has a constructor which takes the value, and then it sets the stored value in that atom. And the get function returns the value, set, and sets the value. So what we can do with those is that we can create those atoms, and we can pass those as arguments and return as results. And the interesting thing is that then program components can declare state as parameters. This is a little bit too simplistic yet to show any interesting examples. So I'll proceed to the next stage. So in the next stage, we can make state observable. So we can implement the atom such that it also is constructed with a value, and it holds the current value. But it also has a list of observers. And we can also, again, get the value, and we can also set the value. But when we're setting the value, then all the observers are notified of the new value. This is really sort of simplified to the core example. In reality, you would have to implement this in a little bit more complex ways to make them really work well. But you should get the basic idea from here. And then we add a new method to this interface, which is really a method from the observable type, which is the ability to subscribe. So we can give an observer, and the observer gets immediately the value from the atom and is also added to the list of observers. So what this observable state gives us is actually independence from time. So if state complex value and identity and time, then this actually allows us to write programs in a manner where we don't have to care about time all the time. So let's see what that actually means. So here's a little. This is actually a sort of a boilerplate project from the Calm open source project, and here we have just a simple empty page. So let's then write a simple component that takes state as a parameter. So let's write a simple text input. And now we can give a value as a parameter to the text input. And then we can create an input with type is text. And then we can show the value. And then we can make it so that the value changes when the input is interacted with. So that's essentially the component. So there's one special magic thing here going on, which is this line. We are actually not importing React from React, but we are actually importing it from the Caret library, which gives us the ability to just put observables into virtual DOM. So here we are actually just putting an observable value as a property to this virtual DOM component or virtual DOM element. And then what happens is that whenever what happens is that the component then subscribes to the value, and whenever there are notifications of changes, then the component will re-render. So let's see what that does. So we'll create a value here, and here's there's this utility library where we can actually create an atom. So this is basically saying new atom with the empty string as a parameter. And then we can create a text input here, and we can give that value to the text input. So what we get here is a basic text input, and we can write text here. And one of the nice things here is that we can, of course, observe that value in other components. So now when I'm writing here, you can see that the text is also reflected in this parent component. And we can also give the same state to another text input. And this is important because now we have like two components that are manipulating the same state. We can use either component, and they both refer to same external shared state. That's the reason why it works. This component here, this text input, is a stateless component. So the first thing we notice here is that when we have observable state, then when we are changing that state, we are just setting the value here, then we are still being completely consistent with that state in everywhere where we are observing it. That's the important lesson here. And also that we were able to just pass the value to as many components as we wanted. We could use it in different ways. We could also return these variables and so on. And that makes it very easy to share state and write complex components. So let's continue. So the next thing we can do is that we can actually decompose state. So what we have here is a very simple implementation of decomposable state. So we create a lensed atom from some existing atom as a source, and then we have a getter and a setter function, and then we just remember all of those. And when we're getting something, then we actually get from the source and then use the getter function to select something from the source. And when we are setting, then we actually do this, that we get value from the source, and we have this value that we are trying to set there, and then we use this setter function to set the state in the sort of the outer, the bigger object. And then we just set that value into the source. So what this allows us to do is that we can store state as a whole. We can store a complex state, like for instance in a Redux store, and we can then just slice an element of that state and give that slice as a parameter to components. So what that allows us to do is that it allows us to make components that don't have to know about the whole state. They just need to know about the state that they're interested in, like the text input. It's only interested in that text value. It doesn't have to know where that text value is actually stored. And it doesn't even have to know whether that text value is actually stored in some atom, or maybe it's stored in a completely different manner. So let's see what that looks like. So let's make something a bit more complex. So let's instead have an object where we have a name and a phone number. And now, of course, we need to pass the state to these text inputs. And we have this ability to view from an atom. I'll explain that in a bit more detail soon. So what we're doing here is we are creating an atom that stores a record or an object with a name and a phone. And then we instantiate two text inputs, one with the name and the other with the phone. And when I'm now editing here, you can see that we are actually building this object. We are just editing the name field here. Or when I'm editing the phone number, then the phone number changes here. So this way we can slice state to components, and again, you can see that the text input was not changed at all. The text input is sort of inherently reusable because it only depends on the value, the value state that it gets as a parameter. And the user of that component can quite flexibly choose where that state comes from. Okay, so how does this actually work? I was talking about those getter and setter functions. So we could also implement that a bit more manually. So we can of course write a function to get, let's say, get a name, and we could write it like this. So now we have a function that gets a name from a record. This is just using the new destructuring syntax. And so if we now get a name from some record, sorry, it was get name. Yeah, I'll make it bigger. So now I can get a name from a record, and I can also write a function to set the name on a record. So I get an object, and then what I do, I get a name and an object, and then what I want to return is this. I'll use this because I don't think that the browser yet has this wonderful syntax for creating objects then I'll just use the old one. So we use object assign, and then I'm assigning first the object that I get, and then a new object containing just the name. So now I can set a name, and that just creates. So if I'll do it like this. So now I have this name in uppercase, and then I'm setting it to this object, which means that I'm creating a new object with the changed name. Okay, now I have these two functions, get name and set name. So the idea here is actually that we can then package those as a lens. The lens library allows us to write a new lens given a getter and a setter. So I can write get name and set name here, and then I can use the lens library to do the same operations. So first of all, I can get with the name lens, and I can also set with the name lens. And of course, writing getters and setters like this would be really boring. So the library actually allows us to simply use strings as object keys. So we can just write. So let's modify the phone for a change. So we can just use strings as these lenses or ways of getting and setting things. So that's what is happening here. This view function is merely creating a new lensed atom that refers to a part of the state. So that way we get an ability to really sort of create a complex state and then slice parts of that state and give that to components. So of course, when you can do something like compose or decompose, then you have to ask whether the other part is also possible. Is it also possible to compose state? And that's also possible. We can create an atom that is a pair of two other atoms. We have the left-hand side atom and the right-hand side atom. And we just remember those. And then when we're getting, then we get from the left-hand side, and then we get from the right-hand side, and then we return an array of those, or a tuple. And of course, we can also set. If we get an array with a left-hand side and a right-hand side, then we can set the left-hand side with the left-hand side value and the right-hand side with the right-hand side value. So we can not only decompose things, but we can also compose things. We can take two separate atoms storing state, and then we can create a new atom that actually modifies those both. And that gives us ability to do some sort of transactionality. So one of the things that's sort of missing from this very simplistic way of implementing this is that in here there should be a bit of code to ensure that this is a bit more transactional, so that, for instance, intermediate state changes are not reported to observers. But it also gives us independence from storage. So in some cases it's quite useful to have, let's say that you have a library that exports some state, and then you want to actually write components that take that state and something else, then it might be useful to be able to compose those together. I could also demo that briefly. So we can, of course, now we have this contact here, which was a single atom. So we can actually create that from two atoms. We could create a name atom. Oh. One of the funny things is that when I'm live coding and talking at the same time, then I always type what I'm talking. So there's actually this helper function called molecule, which allows us to do this basically. It allows us to create a template of values. So now we are creating two atoms and one composed atom. And the nice thing here is that nothing actually changed. We are actually seeing that the same we are having the same compost object being reported here. We could also, of course, log the other values here. So we could log the name and also the phone. So whenever I'm editing the name, then we will see that the name is reported. This is the name being reported here, and that this is the contact object being reported here. And also the same, if I edit the phone, then I get events that the phone is changed, and also the composed molecule. Right. Okay. Do people have questions at this stage? Is there something that remains sort of magic in those previous examples, like you have no idea what is happening? No? Okay.
Pass the whole contact object to the text field property through the view.
Sorry?
There, you still create the views. Should you now use the atoms to pass the information to the text?
I can do that also. Yeah. So basically, if I just pass the name here and pass the phone here, then this is also possible. So now you can see that the thing works the same also. So I just create this compost state, and we can see that the compost state is still sort of changing there because we are logging it. If we would actually leave this thing out, then nothing would actually happen in here, because the way observables work is that if they don't have subscribers, then they don't update themselves. But we can actually still view through those molecules. But yes, did that answer your question? I guess it did. Okay.
At least from like without knowing technical implementation on this, and then like, is there anything like that's completely different from stuff like from the Bacon or CanJS observables?
No, not really. What I'm actually using here is that here I'm actually using Kefir observables, and there's also a version using Bacon observables. So this could also use many other observable implementations. So no, there's nothing special there.
Just one more question, also kind of in macro level. Don't be afraid to mess up yourself and developers who are going to maintain your code for the up, not small up, but big up. If it's a huge up, making the state observable. Of course, probably you would want for the big up use Redux. You would want to use observables for the REST APIs and all this stack. Probably it's going to start using middleware. So isn't it becoming too complicated for the production ops? How do you think? What's your feeling? Not just for the app to show the stuff how it works, or for the small app, but for the real production app.
Right. So the question is that does it somehow become more complex? Too complex. Well, I know that the original app where we started using these techniques is, according to what I heard, is that it nowadays has something like 15,000 lines of code, and from what I understood is that it's working quite well. So I think that it works in bigger apps also. As a sort of funny thing, I like to say that this approach is not good for writing big apps. And what I mean by that is that usually this leads to much smaller amount of code. So if you want to write big apps, you want to write apps with the maximum line count, then you shouldn't use this approach, because this usually is something like 2 or 4 times shorter.
Yeah, I'd like to, at least my feeling is that the benefit is not obvious in small examples because the overhead seems a bit bigger when you just have a couple of lines and you start wrapping just a couple of strings, but when you start combining things, you actually start getting more benefits. That's at least my favorite feeling.
That's a good point. So, so in fact, the example here is really small, but there is no limit to how complex the objects can be. And the nice thing is that all the components only declare what they are interested in. So this text input is only interested in this value. There might be other kinds of inputs, and they really don't need to know anything about the global state. And then the global state is then sliced in like step-by-step fashion through the component tree to those components. So all the components remain quite simple. So actually one of the questions after the presentation that I had mainly on lenses was that is that in bigger apps does this approach sort of become more complex or have some sort of, I don't know, additional complexity? And really the answer is no. I think that when I'm using this approach, then I'm spending more time writing CSS than the other logic of this program. So the state management is really simple this way. The complexity is in CSS. Right. Okay. So the case for global state. So why do you actually want to make state global? So one of the nice things is that when you have state in sort of just one global atom, from where you slice that state to components, then all of your components can be stateless and can be easily composed. And in fact, creating lists of things is very easy because if you have stateless components, then it's easier to make those work correctly. Also, you can inspect global state. So let's say you have a bug there and you wonder what happened, then usually you can just click from the console log and see what the state is, and then you notice that, okay, here the state changed incorrectly, and then you can figure out where that happened. And it's usually quite easy to work things out. Operations on global state can also be tested simply, and there are like two things here. First of all, when you have the state stored in an atom as an immutable value, then you can write functions that manipulate that immutable value, and you can test those like ordinary functions. You just create a value that represents the state before the operation, then you apply the operation and test that the result is what you expect. And also, because that state is actually accessible, so even if you store that state in an atom and you modify it somewhere, then you can still inspect that state. You can still get that state in the test and directly access that state. And it also gives you a robust single source of truth. And there's one thing here that's sort of important. I'll get to that also a bit later in more detail. But the nice thing about state is that it's sort of continuous. It always exists, and if you modify it, then you still get the modified copy. And there's no chance of, like, if you miss some update. So in those text inputs, for instance, let's say that for some reason some events would be missed. So some state changes would be missed, but in the end you will always see the actual state through those components. So they're quite robust in that way. So on the other hand, local state, all of those are sort of reversed. So local state is inaccessible. So if you have a component with local state, then how do you test that state? You can only instantiate that component, and then you can interact with that component, and then you have to somehow see from the interface of the component, which is probably HTML or VDOM, and then you have to somehow from there determine whether that local state was actually manipulated correctly. It also makes composition harder because for a couple of reasons actually. One of those is that when components store state, then you have to be really careful for instance, manage lists of things correctly, so that also the state of the component is moved if a component moves in a list. And also, if you have local state in a component and then you want to share that state somewhere else, then that becomes harder. You have to find some way to get that state outside of the component and to where you want to actually use that state. So that makes composition really harder. And you can only test local state indirectly, like I just said previously. And also, if you have local state and then let's say for some reason you miss some update, then the local state diverges. It no longer reflects sort of the single truth. It's really easy to write bugs that way. For instance, in a recent project, actually, I wanted to write a component that tracked whether the component was in focus, and I used these on focus and on blur callbacks or events that you get. And the problem was that it worked perfectly in Safari, Chrome, and Firefox, but not in Internet Explorer 11. So what can you do? In some cases, Internet Explorer sends those events in different orders or might not send the same events. So it just didn't work. I had to find another solution for that. So a couple of common misconceptions. One of the things, I think there are probably several people in the audience already who might have sort of this misconception, is that the thinking that streams of observables are stateless. So here's an example, and this is like a really sad example in a way. This is from this Yolk project, which was being done at around the same time than when we started using COM. And what I have highlighted there is that it says that this approach is stateless, so that you create stateless components. But if we look at the example here, so which is basically just the usual counter component. I mean, all the user interface libraries always have to have a counter component example. Every one of those has that. So what we have here is the counter component example. We have plus and minus buttons here, and then it displays the count. And the way it maintains that count is here. It has it merges these +1 and -1 streams, and then scans from those. It starts from a value of 0, and then it just sums those +1 and -1 events. And the thing is that this is not stateless. This really is not stateless. First of all, this create event handler function call here, this creates local state. You can see that it creates local state because it doesn't take any parameters. So it has to come up with something from thin air. And the same happens here, and also the same happens here. So we have actually 3 pieces of local state. The nice thing, of course, with streams is that they are observable. So this sort of magically keeps the count updated. That's sort of the nice thing. But this really is not stateless. And if you would instantiate that component twice, then you would get 2 counters. You have one counter that you can increment and another counter that you can increment and decrement independently. So this really is not stateless. That's a really common misconception, and I've encountered that misconception many, many times. This is really not the only example of that misconception. So the truth is that if you're using observable streams and you do a merge and a scan, then you actually introduce local state. And that local state has all the nasty issues with local state that like every other way of introducing local state. So it's difficult to get to that state. If you want to share that state, then you might have to completely reroute the streams in your application. If you have the state inside your component, then you have to move those outside of the component to be able to share those or to test those. And also, it has the problem of diverging easily. So you have to be really careful with how you manage timings. So if you get events in different orders, for instance, then you might get the local state corrupted, and so on. So on the positive side, streams are observable, and they can help to make dependencies more explicit. So if you have like the counter stream, then you can see from the expression that it merges these +1 and -1 streams. So you can see sort of where the changes to that state come from. But it's not necessarily really all that more easier to find out those dependencies. If you have a local variable storing a state atom, then of course you can just look at where that state atom goes, and you can see where changes to that state atom can come from. Also, another misconception is that if you're having all state in a global atom, then what you get is that anyone can just mutate state, and you get a big mess that way. And that's not really true in my opinion. Basically, of course, the fact is true is that if you have a component that has access to some slice of state, then it can of course mutate it. But you can manage things quite flexibly in a way. So for instance, you can scope things. So the text input component, it can only mutate the value of the text input. It cannot mutate the whole application state through that view of just the text value. So components can only mutate the state that you give them as parameters. When I say global state, I don't mean global variables. I mean state as sort of external and as stored outside of those components, not in the sense of having global variables. Also, it's important to understand that when you have a component that takes state as a parameter, then the whole point is that that component can then mutate that state. It can view that state, and it can also mutate that state. So let's say you're writing a big form, and you have components there that take slices of that state. Then of course the point is that those components can then mutate that state. So it should not be a surprise that mutations can come from there. Also, because everything is observable, then, and of course one of the points is that this makes it very easy to share that state. So if you have a component that takes state as a parameter, and then some other component modifies that state, then that component can still observe the state and then act accordingly. So it can update itself and so on. So it doesn't mean that everything becomes out of sync, for instance. So the conclusion. So the really, like I said, I only had sort of one goal, is to maybe help you see state in a different way. So think about where you want to store state, not just whether you want to make things stateless or stateful. And then how do you keep components consistent with state? Because those are the sort of the important questions that you have to think about when you're doing user interfaces, for instance.